Hello everybody. For this video, we're going to talk about this example from lesson 1, the last example that I apparently forgot to cover during that class. Let's take a look, and hopefully the solution here is going to help you on that last problem on your corresponding homework assignment. Okay, so the question here is determine where G of W is discontinuous and identify each of the type of discontinuity. Um, identify the type of each discontinuity, I should say. Um, so to identify discontinuities for a complete function like this, right, like a one, uh, compact form of a function like this, really there's kind of two different type of discontinuity that you will have to work with, because the jump discontinuity rarely come from one single function. It comes usually from a piecewise function. In this case, we do not have a piecewise function, so we can kind of uh, eliminate that option, that possibility, which means the rest of the two possibilities is either a removable discontinuity or a infinite discontinuity, aka vertical asymptotes. Right? Turns out both of these can be discovered using algebra alone just by asking ourselves what is the domain of this rational polynomial. The domain can actually give us both of these possibilities depending on kind of the output, right? The result of that domain, that value that's being removed from the domain, that is. So to do that, all we have to do is set the denominator equal to 0. So we got w squared minus w minus 20, set that equal to 0. And here, this is a quadratic in terms of w. You can choose to use the quadratic formula if you really um, don't want to practice factoring, but here factoring will be the preferred method. So fairly easy to factor. It comes out to be w minus 5 times w minus, plus 4 equals to 0. We can just do a quick check. Negative 5 times w, negative 5w, and w times 4 is 4w. And of course, if you add these, you get back to the negative w. Okay, and from here, we can solve for w. So set that equal to 0. W minus 5 equals to 0. That means w is equal to 5. Set that equal to 0. We get w plus 4 equals to 0. That means w is equal to negative 4. Okay, so we know our two discontinuities happen at 5 and at negative 4. The question is, how do we identify these? The easiest way to do this is to actually simply plug this in, right? AKA trying to apply the direct substitution method. In other words, if I'm working on, say, w equals to 5, what I'm really going for is the limit as x, or w rather, approaches to 5. And then with my g of w, I'll just write it out. W squared plus 4w all over w squared minus w minus 20. If you plug this in and you get a 0 over 0, then we're dealing with a removable discontinuity. If you plug this in and we get a non-zero number over 0, then you have an infinite discontinuity. Again, a vertical asymptote. So let's go ahead and plug that in. Plug in the 5. We get 5 squared, which is 25, plus 5 times 4 is 20. All over, on the bottom, we have 25 minus 5 minus 20. Of course, that's going to give us 0, because that's how I found the 5s to begin with. So the answer here is 45 over 0. So in this case, what? We have a non-zero number over 0. So we have uh, so we have an infinite discontinuity at w equals to 5. Okay, and again, this infinite discontinuity really comes from the fact that the limit is approaching to infinity on either left or the right side, from the left or the right side of 5. infinity or negative infinity, right? We talk about that actually in the next section, but hopefully, you kind of already see that video by this point. Going on to the second one, w equals to -4. Again, same idea. We're just essentially evaluating w approaches to -4 here, and that's going to give us, again, w squared plus 4w all over w squared minus w minus 20, and that's equal to -4 squared is 16, plus 4 times -4 is -16, all over, we got 16 plus 4 minus 20. Again, the plus 4 is because -4 is positive 4. So overall, we get 0 over 0. In fact, we kind of already know what 0 over 0 means in this case. We have a removable discontinuity. But let's just play this out, right? Let's play this out. It also serves as a good example for what happens during the removable discontinuity. Is we can simplify. So this equals to limit as w approaches to -4. And the top factors into w times w plus 4. The bottom factors into w plus 4, w minus 5. And we can easily see that we have a cancellation here, right? W plus 4, W plus 4 cancels out. So this becomes limit as W approaches to -4, W over W minus 5. And now if you plug in W equals 4 again, -4 again, you get -4 over -4 minus 5, which is then give you 4 over 9, right? The double negative cancels out. So the point here is, for a removable continuity, we can actually get a limit of the function such that if we go ahead and just use a piecewise function to plug in that hole, I can essentially remove the fact that this part is discontinuous. Okay, so again, this right here, this indicator is a big indicator that it could be a removable discontinuity. Now, this doesn't automatically imply it's a removable discontinuity, because you could have simplified, right, and you realize there's another factor of w plus 4 on the bottom, right, for the sake of example here. But typically, when you have 0 over 0, it's a big indicator that it's potentially a removable discontinuity. Anyways, let's go ahead and conclude this video by finish writing this. So we have a removable discontinuity at w equals to -4. Okay, so that's it for this video. Hopefully this helped, and if you're having questions, feel free to let me know.